Hello viewers, welcome once again back to my channel Math Made Easy with PDY. Thanks for your subscription to my YouTube channel, my Facebook channel, as well as my Telegram channel. If you want to get in touch with me, I would like you to reach me on Math Made Easy with PDY on the Telegram channel for live math lessons. Now, without wasting my time, I would like us to move on to today's topic, which is differentiation, derivative of function, or derived function. But our subtopic for today is actually looking at derivative of functions from rules or from formulas. I'm not going to teach you the formula, but I'm going to show you a very simple way of getting the derivative of functions found. So in our previous lesson, we actually looked at finding the derivative of function from first principle. And we found out that from first principle, if I have a function given as, let's say, f of x equal to x squared, and I'm asked to find the derivative of this function from first principle, we found out that then we have to introduce the small change in x, and that is our function is going to be x plus h all squared. Then from first principle, we learned that it is given as dy dx is equal to limit as the small change in x approaches 0 for the function f of x plus h minus f of x, all divided by h. Then in this case, per our expression written here, we can write our substitution to obtain dy dx, which is the gradient of the function, to be limit as h approaches 0 for f of x plus h has been given as x squared. When you expand x plus h all squared, you are going to obtain x squared plus 2xh plus h squared. Then this function minus f of x, which is x squared, then all divided by h. So going further, to simplify this expression, at this point you can't substitute the value of h into the function because it will give you undefined solution. But going further, we'll actually have x squared here minus s squared, and that will be given as 0. So it will be left with limit as h approaches 0 for 2xh plus h squared all on h. So at this point, since the substitution still can't be possible, then we have to reduce this function in the form that we can do away with the h at the denominator. So we need to factorize out. So we'll have limits as h approaches 0 for h out, then 2x, because h multiplies 2x to give us 2xh, then plus h, because h multiplies h to give us a squared, all divided by h. Therefore, we can do away with the h, and it's going to be left with dy dx equal to limit as h approaches 0 for 2x plus h. At this point, you can substitute the value of h, which is 0, and we are going to obtain it as dy dx will be equal to 2x plus 0, and 2x plus 0 is the same as 2x. So it tells you that the derivative of this function x squared is given as 2x, and hence in simple way, without going through first principle, if you look at it carefully, you realize that it's a very simple trick. If you consider the function y equal to x squared, finding dy dx directly without using any first principle concept, to get the 2x, you just simply pick the power of the variable x, multiply it by the coefficient of the variable x, and that is going to give us 2 multiplying 1, which is the coefficient, that will be 2. Then we subtract 1 from the power, so we are going to get x, and that will be all. So that's a very simple way of finding the derivative of a function without going through any first principle. So in short, we can say that simple derivative, if I have y equal to kx to the power n, then for simple derivatives, we can say that then dy dx will be equal to, pick the power of the variable x, multiply by the coefficient, and that will be given as kn, and then subtract 1 from the power, which will be x to the power n minus 1. And this is a very simple idea you can use to determine the derivative of a function. A simple derivative rule which you can apply. Pick the power, multiply by the coefficient, subtract 1 from the power, and that will be all. Let us take some work example on this. Let's assume that we have some work examples as that. Find the derivative with respect to x. So we are taking number 1. I'll take just a few of them, then you can do the rest later. So having y equal to x to the power 7. So dy dx will be equal to, select the power, multiply by the coefficient. So this will be given as 7x, then subtract 1 from the power, that will give us 6. So the derivative of this function is 7x to the power 6. Then again, we come to a perfect example. Let's take question number 8, which is y equal to 3 on x to the power 4. We can change this to apply the simple derivative rule by simply changing the fraction into a power form. So it will be y equal to 3x to the power negative 4. If you go back to your indices, you realize that this function can be written as that. So from the basic derivative or the simple derivative, then dy dx will be given as negative 12, because negative 4 times 3 will give us negative 12. Then x, subtract 1 from the power, will get negative 5. And in this case, you can write it back to the fraction form. Then it will be negative 12 on x to the power 5. So the derivative of this function gives us what is there. I would like you to give it a try to find the derivative of all these examples here from simple rule, and then give me a feedback in the comments below. Let's go to the next example. So now we are looking at differentiating polynomial functions. Differentiating polynomial function, the simple way you can use, you can differentiate a polynomial function. Now, without wasting my time, we learned some time ago that polynomial functions are of the form, let's say f of x is equal to, let's say, ax cubed plus bx squared plus cx plus d, and it goes on and on and on. Now, this kind of polynomial function, one characteristic of a polynomial function is that the power of the variable under discussion reduces in order of magnitude, or it increases in order of magnitude. So addition sign and subtraction sign separates the two functions altogether. So let's take it that I have a very simple derivative as f of x equal to probably 3x squared plus 2x plus 5. Now, in order to differentiate this kind of polynomial function, you realize that you can take it that this function is equal to that, added to the same function equal to that, added to the function equal to the third term. So you can take it term by term and then actually find the derivative of the functions, and then you bring them back together, and it gives you the derivative of the function for the whole function all together. So in other words, if I take it term by term, so if y is equal to 3x squared, then dy dx will be equal to, this will be given as 6x. Then when I pick if f of x is also equal to, or let's say y equal to 2x, let me use y because that's what I've been using so far. So let me use y. Let me use y. So I have y equal to 2x, then dy dx will be equal to 2. Then finally, if I have y equal to 5, remember from first principle, we learned that when you find the derivative of a constant, yes, what do you say? You obtain what? 0. So now, after finding the derivative of each of the functions, then I can bring them together, and therefore, the derivative of the function altogether, dy dx, will then be equal to, I have it as 6x plus 2, then plus 0. But you know, that is finally written as 6x plus 2. So whether it is subtraction or addition, as long as it's a polynomial function, when you are asked to find the derivative of the function, take it term by term. Then use simple derivatives to determine the gradient of the function or the derivative of the function. Then you bring them back together, and that will give you the general derivative of function for the whole polynomial function. So please take note of that. Take note of that. Lest I forget, when we come to, there are so many symbols used to represent derivative of functions. So if I have f of x, I can write it, if I want to write the derivative of the function, it can either be written as f prime of x. If I have it as y, it can be written as y prime, which is first derivative. And then if I have it as, so if I have it as y again, we can also write it as dy dx. Then we can also have it as y given as d dx. There are so many symbols that we can use to represent the derivative of function, but the one which is most convenient for students is always they saying dy dx. But please take note, you can see f prime of x or y prime or d dx. They all represent derivative from the first derivative of the function, Okay, so let's take some basic examples on how to differentiate polynomial functions. So with this, we have an example here. Differentiate each of the following with respect to s. All these are perfect examples from question 1, 2, and 3. They are perfect examples of differentiating polynomial functions. Question 4 needs to be expanded, simplified before you can differentiate using the simple derivative. But let's take it and then let's see the way forward. I will just take a few of them, then you try your hands on the others. So for the first example, if I have y equal to s cubed plus 2s squared plus 3x, now to find dy dx, or the derivative of the function with respect to x, as I said, take it term by term, differentiate it from using simple derivatives, and then you bring them all back together. So this is giving us 3x squared. You pick the power, multiply the coefficient of the variable x by the power, and that is giving us 3. Subtract 1 from the power, so that is 3x squared. Then plus, this will give us what? 4x, multiply the power by the coefficient, giving us 4. Subtract 1 from the power, that's 1. And then plus, this will be leading us to 3. So that is all. Now that's number 1. If we consider question number 4, let's take number 4. So y equal to 2x minus 3, or multiplying 1 minus 5x, or divided by x squared. So to find dy dx, before I do that, as I said, I have to write it in a very simple way. So y will be equal to, then I expand the numerator, that will be giving me 2x minus 10x squared, then minus 3, then plus 15x. Simplifying this expression, all divided by x squared. So y still becomes, final simplification will give us negative 10x squared. Then we have plus 17x, then minus 3, all on x squared. So at this point, I'm going to write it term by term. So I divide through by x squared. So that will be giving me y equal to 10x squared, negative 10x squared divided by x squared, it will be left with negative 10. And then 17x divided by x squared, it will be left with plus 17 over x. Then finally we have negative 3 on x squared. So to write it in the power form, y will be equal to negative 10 plus 17x to the power negative 1, then minus 3x to the power negative 2. So I've written it in a form whereby I can easily use the simple derivative to work it out. So dy dx, or y prime, as I said, will be given as the derivative of a constant is 0. So we have 0. Then over here, negative 1 multiplied 17 will be left with negative 17x. Then we subtract 1 from the power. So that will give us minus 2. Then negative 2 multiplying negative 3 will give us plus 6x to the power. Subtracting 1 from the negative 2 will give us negative 3. So my final dy dx will be given as negative 17 over x squared, then plus 6x raised to the power positive 3. So my dear friends, I believe you can actually do this in other ways, but as I said, I'm not using formulas, but I'm using the concept to work out everything here. So there's no one way of solving the question unless you are just stuck somewhere and you can find your way out using other means. Okay, so going to the next. So please try your hands on the other ones, and I believe you are going to be fine on that. Going to the next, we are going to differentiate functions which has been expressed in a factor form. Functions expressed in a factor form. So let's take it that we have, let's say, f of x equal to x plus a, all multiplying x plus b. So when you have function written in a factor form, you can see that they are multiplying. So in this case, we are going to apply a simple rule known as the product rule. And how does the product rule works here? Instead of quoting a formula, just understand the process. So to find the derivative, let's take it that you have the function as this. The first factor, you just have to note it as, if the first factor is u, then you have x plus a equal to u. Then the second factor as v, then x plus b is equal to v. So it means your y is equal to uv. That is a very simple way of writing this expression. So what is the process with respect to the product rule? How do we apply the product rule? So applying the product rule. Since it's in the factor form, to find dy dx, the first thing you have to consider is maintain the first function. So maintaining the first function, so we maintain it as it is, we just put it down as it is. So we maintain u. Then find the derivative of v. So we are finding v prime. Like, I explained how you can write the derivative of the function. So v prime. Then you add on the reverse of the operation that we did early on. So the reverse of the operation is maintain this time around the second function, which is v, and then differentiate the first function, which is u prime. And in this case, if you work it out, you realize that this gives you the derivative of the whole function all together. Because of time, I can't go back to explain, but if you go back to my previous video whereby I showed you differentiating giving factors using first principle, you realize that everything spells out clearly. And you realize that this process works perfectly. This is what people term as formulas, and they do use. But as I said, follow the procedure and you'll be fine. Just first consider the first function, maintain it as it is, differentiate the second function, add it to maintaining the second function and differentiating the first function, then you find the product of them, add everything together, then that gives you the derivative of the whole function all together. And that is what we term as the product rule. The product rule. So let's take some work examples on that. All these examples here are perfect examples of product rule. Product rule. Even though you could have also used the simple derivative to work it out by first expanding and simplifying in their power form, and then now use a simple rule. But if you want to also go further and faster, you can also apply the product rule. So I'll take two examples, then you try your hands on the others and give me feedback on that. So if I consider question number 1, if y is equal to 2x plus 1, or multiplying 3x minus 2, so dy dx will be equal to maintain the first function, which is 2x plus 1, then multiply it to the derivative of the second function. So this is my u and that is my v. So I'm differentiating the second function. So differentiating the second function, which is the one in the bracket here, 3x minus 2, you realize that it's a polynomial function, so can differentiate it term by term. So that is going to give us, differentiating 3x will give us only 3, and differentiating negative 2 will give us 0. So we've done differentiating the second function. Added to maintaining the second function, which is 3x minus 2, multiply to the derivative of the first function. So 2x plus 1, when you find the derivative of it, you are only going to obtain 2. Because when you differentiate 2x, you get 2, and differentiate 1, you get 0. So expanding and simplifying will give us a final answer as 3 times that will give us 6x plus 3, then plus 6x minus 4. So putting them all together, we have 12x. 3 minus 4 will give us negative 1. So we've used the product rule to work out this, and it's giving us a final answer. We've not quoted any formula. We've just gone directly, and it is accepted in any field of mathematics. Okay, so taking another example, let's take question 5. Question 5. So having y equal to, into bracket, x squared minus 3x plus 5 multiplying 2x minus 7. Just imagine you are being asked to use first principle to work this out. My dear friend, you actually write long pages to get a final answer, but we want to get this done without first principle. So in this case, we are using product rule to work it out as well. So dy dx will be equal to maintain the first function, that is x squared minus 3x plus 5, then differentiate the second function, which will give us 2, added to maintaining the second function, which is 2x minus 7, differentiating the first function, that will give us 2x minus 3. Then now we expand, plus 0. Then now we expand and simplify. Final, that is going to give us 2x squared minus 6x plus 10. Then plus 4x squared minus 6x, then minus 14x, then plus 21. So putting them all together, we have 2x squared here, 4x squared. That will give us 6x squared. And then we have negative 6x. And then we also have negative 6s. And then another. So that is giving us negative 12x. Negative 12x plus minus 14x will give us negative 26x. So we have minus 26x. Then 10 plus 21 will give us plus 31. So that is the derivative of the function using actually what we say the product rule. Please, you can give it a try using also the simple rule by first expanding and simplifying before you differentiate. It will give you the same answer. Let's go to the next. So we are now looking at rational functions. If you have a rational function and you are asked to differentiate, how do you go about it? Let's say that we have the function as f of x is equal to g of x all on h of x, where h of x is not equal to 0. So that is a rational function. So how do you go about differentiating rational functions? If per investigation you realize that if you are differentiating rational functions, if you want to find dy dx of that or f prime of x, the process looks a bit different from that of the product rule. We this time around use what we call the quotient rule. The quotient rule. And how does this quotient rule works? The process is, as I said, slightly different from the product rule. So the quotient rule works as this. First, maintain the denominator, which is going to give us h of x. Now let me use simple symbols to represent that so that we don't write so many variables. So let's take it that f of x is equal to u over v. Yes, g of x is u, h of x is v, where v is not equal to 0. So dy dx, or let's say f prime of x, will be equal to, this time around, the quotient rule works as this. Maintain the denominator, which is v, multiply it to the derivative of the numerator, which is u prime, minus maintain the numerator, which is u, multiplied by the derivative of the denominator, which is v prime. So it's the reverse of the product rule, but this time around it goes with subtraction. Then finally divided by the denominator squared, so v squared. And that is the whole idea of the quotient rule. I'm going over again. First, in order to apply the quotient rule, maintain the denominator, which is your v, differentiate the numerator, so you have u prime, minus maintain the numerator, which is u, differentiate the denominator, v prime, divided by the denominator squared, so v squared. That's all. So don't choose this as a formula, but understand it as a process and then apply it in solving questions. So let us look at it as fast as we can. So this is a perfect example of a rational function. All these are examples of rational functions. So I'll just take two examples and then, as I said, we move on. Considering y equal to s squared over x minus 1, to find dy dx, we said first maintain the denominator. So our denominator is x minus 1. We maintain it as it is. Differentiate the numerator. So we are multiplying to the derivative of the numerator, which is going to be 2x. Good. Minus maintain the numerator, which is x squared. Multiply to the derivative of the denominator. So when we differentiate the denominator x minus 1, what are we going to obtain? We are going to obtain 1. Then all divided by the denominator squared, which is x minus 1 all squared. Expanding and simplifying, we are going to have dy dx equal to, that is 2x squared minus 2x, then minus s squared, all on x minus 1 all squared. Going further, we'll have it as 2x squared minus s squared will be left with x squared, then minus 2x all over x minus 1 all squared. You can choose to leave the answer in the factor form by factorizing out where necessary and reducing it where necessary. So if I should go further, I can have it as dy dx is equal to, because there's a common factor between the numerator terms, so we have x out into bracket x minus 2, then all divided by x minus 1 all squared. So the answer might be left in this form or that form, or even the denominator can be expanded. Just be ready for anything altogether. But in all, the derivative of number 1, the answer is either this or that, and that is how simply you can do it. It is not necessary that you always expand the denominator because it has been increased to a given power. No, it's not always necessary. Let me take let's say example number 6 into consideration. Like, you can try your hands on all of them, but let me try example number 6 with you. So considering example number 6 on a different page, if we have y equal to s squared plus 1 all on s cubed minus 1, because we just seen directly it is rational function, dy dx will be equal to, maintain the denominator s cubed minus 1 multiplied by the derivative of the numerator, that is differentiating the numerator, will get 2x plus 0, then minus maintaining the numerator, which is s squared plus 1, differentiating the denominator, we will get 3x squared plus 0, then all divided by x cubed minus 1 all squared. Going further, we expand the numerator and simplify. So we are going to obtain 2x to the power 4 minus 2x, then minus into bracket. That will give us 3x to the power 4, then plus 3x squared divided by x cubed minus 1 all squared. Final expansion and simplification will give us 2x to the power 4 minus 3x to the power 4, then minus 2x, then minus 3x squared, all on s cubed minus 1 all squared. Then finally we can simplify, and dy dx will be giving us an answer of negative x to the power 4 minus 3x squared minus 2x, all on x cubed minus 1 all squared. As I said, you can leave the answer as this, or you can factorize where necessary, and then that will be all. Okay, thanks so much. Let's move on to the last but not least. We are looking at composite functions. We are looking at how to differentiate composite functions. How to differentiate composite functions. So when you consider composite functions, they are simply functions within another function. And in this case, this is the kind of function written whereby a given function is raised to a given power. So for instance, if I have f of x equal to g of x all raised to the power, let's say n. This is a perfect example of a composite function within another function. So you can have examples like f of x is equal to x plus 2 all squared. This is a composite function. And how do you differentiate it? You can work it out using other ways, or you can also basically go with what we call the chain rule. You can go with what we call the chain rule. So with respect to the chain rule, how do we apply the chain rule in working out such a function? So if I have a composite function as this, to find dy dx, I first need to differentiate what is outside the bracket. So outside the bracket, then it means I have 2 into bracket x plus 2, then subtract 1 here, because you maintain what is inside the bracket, but you differentiate what is outside the bracket. So you are differentiating outside the bracket. Then you multiply this first function with the differential of, let's say, the inner function, and that is going to give us, the differential of this is giving us what? 1. Because when you differentiate x, you get 1. You differentiate 2, you get 0. So finally, you are going to obtain it as 1 times 2 is 2. So you have it as 2x plus 4 as a final answer. Now you could have worked this, and that's the composite function rule. Differentiate what is outside the bracket, multiply it to the derivative of what is inside the bracket. Again, differentiate what is outside the bracket. So let's take it that I have f of x equal to, let's say, v raised to the power n. V raised to the power n. First, I'll differentiate what is outside the bracket. So dy dx, or f of x prime, or f prime of x, is equal to, differentiate what is outside the bracket. That is going to give us n v to the power n minus 1. Then multiply it to the differential of what is inside. So you are going to differentiate what is inside the bracket, which is going to be v prime, and that is all. Then you expand and simplify where necessary, and that is what is known as the chain rule. The chain rule, because of the multiplication, chains are in the form of multiplication here and there, so that is why we applied. So let's take some examples on that. These are perfect examples of composite functions for which we can apply the chain rule. So let's take number 1 and probably number 2, and then we'll you try the others and give me a feedback on that. Where you have a challenge, just inbox me and I'll help you out. So we have y equal to 2x plus 3 all to the power 4. So dy dx will be equal to, differentiating what is outside the bracket will give us 4 into bracket 2x plus 3, then to the power 3. You subtract 1 from the power, multiplying the derivative of what is inside, that will give us 2. Expanding and simplifying, I'll have it as 2 times 4 giving us 8 into bracket 2x plus 3 all raised to the power 3. It is not necessary that I need to expand this function to the third power. No, you can leave the answer as this and it will be marked for you. It's accepted. It's accepted that way. Okay. Again, we have a surd function, so which is a function under the radical sign. So having it as y equal to square root of 2x squared minus 5, then dy dx, before that, write it in the power form whereby it will be easier for you to work it out. So y is equal to 2x squared minus 5 all to the power half. And in this case, that will be giving us y prime is equal to half of 2x squared minus 5 raised to the power, subtracting 1 from half, we are having negative half. Then multiplying to the derivative of what is inside, we will get 4x. We'll get 4x. Expanding and simplifying, 4x multiplying half will give us actually 2x into brackets 2x squared minus 5 all raised to the power negative half, for which this answer here can be left also as, based on indices, you can have it as y prime or the y dx is equal to 2x all over square root of 2x squared minus 5. 2x squared minus 5. My dear students, I'm so happy coming your way with these simple examples. I would like you to try your hands on more examples and then give me a feedback. Thanks so much for joining the call, and kindly subscribe to my channel if you haven't. God richly bless you. Have a nice day. Bye bye.